Alright, welcome to geometry class. In this class, we'll solve a ton of problems involving geometry. We'll learn a lot of geometry, especially geometry that is not learned in the classroom. And we'll learn a lot of techniques and theorems and concepts in order to solve some of the hardest geometry problems that you might see in competitions. My name is Mr. Goobles. You can also call me Austin. And the course information, this runs for 3 weeks, Monday through Friday, 2 to 4 p.m. Oh, actually, that's supposed to say 2:30 to 4:30. Yeah, so it's 2:30 to 4:30 at Gear Library. And the first 2 days are on YouTube, and we start meeting in person on Wednesday. And as far as materials go, just make sure to bring a notebook, something to write with, and a folder. You'll definitely want to bring a folder because we'll have a lot of handouts. And there will be daily homework problems, so be prepared to solve problems in your evenings, and they'll range from easier to pretty difficult. And just know that you may not be able to solve all the homework problems, especially as we move into the later chapters. This is perfectly normal, so don't worry if there are problems you can't solve without help. That's perfectly normal because we're going to cover lots and lots of hard problems. So I'd actually be concerned if you never had any struggle whatsoever. You definitely are going to struggle. Some problems will be easier than others, but just try your best, and that's all I can ask of you. So yeah, class today and tomorrow will just be a brief YouTube video covering the content. It's not super high quality videos, but it gets the concepts and gets the material over. So let's get right into the course structure for this class. So today we're going to talk about everything to do with circles and angles, all of the concepts involving circles and angles. Tomorrow we'll talk about triangles. Wednesday we'll do trigonometry and area. And Thursday we'll do quadrilaterals. And Friday we'll do polygons and angle chasing. And then this weekend, we'll have some homework, a longer homework assignment than the other days because you have a weekend to do it. And then week 2, Monday we'll talk about area. Tuesday we'll impose a coordinate system and we'll do some problems with that. Wednesday we'll talk about a super important theorem called power of a point, and we'll solve a bunch of problems where you apply that. Thursday we'll talk about 3 dimensions and do problems in 3D. And then Friday we will just work through problems the entire time. And there'll be a ton of problems that we'll have for homework as well as we'll do in class. And then, of course, we'll have a weekend assignment. And then week 3, on Monday, we're going to learn some more triangle theorems. On Tuesday, we'll talk about cyclic quadrilaterals, which are quadrilaterals where the vertices all lie on a circle. On Wednesday, we'll talk about Menelaus's theorem, Stewart's theorem, and Siva's theorem. And then on Thursday and Friday, we'll take a couple days to cover the technique of mass points geometry. Mass points geometry is based off a principle of physics, and it's incredibly useful when solving triangle problems where you have cevians and you're asked about ratios of lengths. So yeah, I hope this outline looks exciting. We'll solve a ton of problems, and again, if some of these concepts look too easy, we will solve a lot of problems that range in difficulty. And if you've never heard of some of those concepts, that's great, because we'll cover them and then you'll know about them. So let's jump right in. It'd be great to take notes if you have a notebook with you. So to start off with, a circle is defined as the set of all points which are a fixed distance from a specific point. The specific point in question is called the center, and we have a little diagram on the right. There's center O of this circle, and we usually call a circle by its center. So if we talk about circle O, we're meaning the circle that the point called O is the center of it. And of course, the distance, that fixed distance that all the points on the circle are away from the center, is called the radius. And we can call the radius OA because it's a line segment that starts at O, ends at A, or vice versa, starts at A, ends at O, whatever. A chord of a circle is going to be a segment whose endpoints are both on the circle. So a chord can be like line segment AC there. Line segment AC is a chord. Also a diameter is a chord, so line segment AB. Any line that passes through the entire circle is a chord. So a diameter is just a special case of a chord, but really a chord can be anywhere on the circle. Another way to say this is that a diameter is a chord that passes through the center of a circle. If you have a chord passing through the center of a circle, it must be the diameter, and vice versa. If you have a diameter, it must be a chord that passes through the center of a circle. A tangent line in the picture denoted by line L. A tangent line is a line that touches a circle in exactly one spot. Exactly one spot. And we'll learn a little bit later today that if you have a tangent line to a circle, if you draw another line from the point of tangency, so point A in the picture, if you draw a line from point A, the point of tangency, to the center, it'll always be perpendicular to the tangent line. So another way to think about it, if you think about the tangent line being the ground, and if you rotate the image so that line L is horizontal to the ground, you'll see that, well, the center of the circle has to be directly above. So that's always going to be perpendicular. So line segment AO, line segment AB, whatever, any line that passes through the center that starts at the point of tangency is going to be perpendicular to the tangent line. A secant, line M in the picture, a secant is a line that goes through the circle and passes through it at 2 points. So a tangent line just barely touches the circle, but a secant line goes through 2 points. You can also think of it as a chord that's extended forever, because a line technically goes on forever, but a line segment stops. Another important word is the word concentric. If you have multiple circles in the same diagram, circles are called concentric if they share the same center. So they may be different sizes, but they're concentric if they share the same center. And it'll always be pretty obvious if they're concentric or not, because concentric circles always are directly inside of each other, and it's very clear that they have the same center. An arc is a connected portion of the circumference of a circle, and we can call it arc AC if A and C are the endpoints of the arc. And since AC could refer to two different arcs, right, the smaller arc or the larger arc, we generally refer to the major arc as the larger one and the minor arc as the smaller one. So unless otherwise specified, always assume the minor arc is meant, just because that's usually what we need in a problem, is the minor arc. Unless otherwise specified, assume the minor arc is meant. Okay, so very often we can use 3 points to specify an arc, and that'll erase any ambiguity about whether we do the minor or the major arc. So we could call arc ABC the major arc AC, where the middle point is the point that's in between the two other points. So if you do arc ABC, you just look at points ABC in order, and that's the arc that's being referred to. Also, the area inside of a circle that's cut off by 2 radii is called a sector. So you can also think of a sector as a piece of a pie. It's just going to be 2 radiuses, any 2 radii that cuts off a piece of pie from the circle. That's called a sector. And a circular segment is the area between a chord and the arc that it intercepts. So what we mean by a chord intercepting an arc is just a chord is going to cut off part of the circle, and that we can call that the arc that the chord intercepts. What's probably familiar to you already is the area of a circle is pi r squared, and the circumference of a circle is 2 pi r. So just as a quick example problem, please put your answer in simplified form as as the correct answer, not as a decimal approximation. But if you have pi in your answer, make sure it's in there. What's the maximum area that can be enclosed by... Oh, sorry, whoops. The area of a circle is 16. What is the circumference? So take a few moments to figure that out. All right, here's the solution. If you let the radius of the circle be r, we have the area of the circle is 16, so pi times r squared is 16. Divide by pi and then take the square root, and we get that r is 4 over the square root of pi. Thus, we have the circumference is 2 pi times that quantity. So 2 pi times 4 over root pi is going to be 8 pi over root pi. But if we rationalize the denominator and multiply by the square root of pi over the square root of pi, we're going to get 8 times the square root of pi. So let's try another example real quick. What's the maximum area that can be enclosed by 12 feet of fencing? Okay, hopefully you had enough time to work out that problem. So we start with the perimeter. We have a certain amount of fence. We have 12 feet of fencing. The largest area that can enclose is going to be a circular area. So we'll just think about the feet of fencing that we have as the circumference. So the circumference is 12, so 2 pi r is equal to 12. So if we solve for r, we get 12 over pi. I'm sorry, not solve for r, but solve for 2r to get the diameter. We'll get 12 over pi, and then the radius is 6 over pi, and then we can just take that squared times pi to get the area of that circle. We get 36 over pi. Okay, let's try these next 4 problems. I'll give you some time to work on this, and then we'll talk about each of these, and we'll see how you did. All right, hopefully you had some time to work on these problems. Um, Here's the solutions. So the first one, we know that the area is 8 pi. The radius is therefore going to be the square root of 8, which is simplified as 2 root 2. So the circumference is 2 pi r, and we know the radius is 2 root 2. So we get 4 pi root 2. For the second one, this one's a little bit tricky if you don't see it right away, but here's a way to do this. So if we let little r be the radius of circle C and little s the radius of circle B, then segment BX as a radius of circle B has length s. Thus, AX is equal to 6 plus s. And then we also know that AY is equal to 5 plus r. And since these are both radii, we can set them equal to each other. And so then we can get an equation from that. So 6 plus s equals 5 plus r. And we also know we have another equation. We have that BC is equal to r plus s, but that's equal to 9. So we have a system of equations, two variables. You can solve it however you like, but when we solve it, we get r equals 5, and then we get the radius of the other circle is just 5 more than r, so 10. Now for the third problem, both of the pieces have to have length 36 if they're of equal length, and they're made into circumferences of circles. So circumference is pi times diameter. So to get the diameter, we can get 36 over pi, so then the radius is 18 over pi. And so each of the circles is going to have area 18 over pi squared times pi, or 324 over pi. So we just add those two together, so we just double 324 over pi, and we get 648 over pi. And then now finally for the fourth problem. So if we just give names for the three radii of the three circles, we can give them names r, s, and t. And we can also give names to side BC, AC, and AB. So from that we have a few equations. A is s plus t, B is r plus t, and C is s plus r. And if we're trying to find r in terms of ABC, well, if we add the three equations, we're going to get a really nice equation. A plus B plus C is 2 times r plus s plus t. And then if you subtract s plus t equals a from that, to cancel s and t, you're going to get r equals b plus c minus a all over 2. So that's kind of the solution to 4 in the neatest form. The way you might actually do this in practice, you might just try to get r by itself, which is totally fine, because we know that we know that we can replace s and t with their appropriate a, b, and c, whatever they're equal to in terms of a, b, and c, and it turns out that, well, s and t, well, s plus t is equal to a, so you can easily substitute that in. Okay, so that was a few problems that we could do just with knowledge about circles and the parts of circles and a little bit of algebra, but not much else. Momentarily, we're going to move into the study of angles. So the art of problem solving has a nice chapter on angles, so we'll just cover the content in this. And the angles, you know what an angle is, of course, but there's many different parts of angles and many different concepts that we need to know about with regard to angles. So let's just get right straight to it. Let's start out by talking about a line, a ray, and a segment. Obviously, the little picture here, there's a line segment AB, there's a ray CD, and a line EF. Just that, a line goes on forever, a line segment stops, and a ray is a line segment that's continued in one direction. Okay, you should know that any 2 points can determine a line. That just means that if you write down any 2 points or draw any 2 points anywhere, you can always connect them with a line, and there's only exactly one line that will go through those 2 points. If you have multiple points on the same line, we say that they are collinear. And we know that for collinear points, we can add the lengths like ax plus xb equals ab, just like that, because they lie on the same line, and so we can add their lengths like that. Okay, so moving on to an angle. Two rays that share an origin form an angle. So that's technically the definition of an angle. It's two rays that emanate from the same starting point. We call the rays the two sides of the angle. And the common origin of the two rays is called the vertex of the angle. So if we consider a circle centered at the vertex as shown below, in that little picture there, we say that the angle subtends the arc it cuts off. So an angle is denoted by the little caret symbol, the little angle symbol, as an angle AOB. And a really important and crucial point, the vertex always goes in the middle. So whenever we talk about angles, the middle letter is always going to refer to the vertex of the angle. When there's only one angle with the given vertex, we can just use the vertex to name the angle. As in this picture right here, it's totally fine to just call that angle O. But if there are multiple angles that have O as a vertex, we need to specify using 3 letters instead of 1. An angle, we can always measure it in degrees. There's 360 degrees in a circle, so the angle is going to cut off a quarter of the circle if it's 90 degrees. And if it's 45 degrees, it'll cut off an eighth of the circle. The number of degrees in a circle is rather arbitrary. 360 is just a highly divisible number, and it's always used for historic reasons. Yeah, so the reason that it's not 100 or some other number is because 360 is highly divisible. So we can cut it into thirds, fourths, things like that. Also, portions of a degree we can talk about. So we can apportion a single degree into 60 different parts called minutes, and we can apportion a minute into 60 different parts called seconds. So there's 60 minutes in a degree and 60 seconds in a minute. So if you want, you can think of a degree as kind of like an hour, and we can cut it into minutes and seconds if we want to. Now we'll rarely do this in practice, but it is good to know this. So an angle with measure 0.5 degrees, we'll just have a measure of 30 minutes. An angle of 20 degrees, 10 minutes, and 5 seconds is written 20 degrees, 10 minutes, and 5 seconds. So kind of like feet and inches, except we're going to talk about minutes and seconds here. So we can also measure a degree by radians. So if you haven't heard of radians before, it's just another way to measure the angle. So since there's 360 degrees in a circle, we're going to say that there's 2 pi radians in a circle. And that comes from the fact that the circumference of a circle is 2 pi r, meaning that if you take the radius of a circle and you lie it around the circle 2 pi times, that's the 2 pi is the amount of times that it will fit around the circle. So a radian is kind of a natural, it's just the angle you get by laying a radius down on the circumference of a circle, and that's the angle you get. So you can use a conversion factor to go from degrees to radians and radians to degrees. If we start off with radians, to make it degrees, you just multiply by 360 over 2 pi. And if you start with degrees and you want to get to radians, just multiply by 2 pi over 360. So an example question, how many degrees are in pi over 3 radians? We just take pi over 3 times 360 over 2 pi to get 60 degrees. How many radians are in 135 degrees? Just take 135 times 2 pi over 360, and that will get you the number of radians. So we have that pi over 3 radians is 60 degrees, and 135 degrees is 3 pi over 4 radians. And again, we're just multiplying by 1, basically, because 360 degrees is equal to 2 pi, so we're multiplying by 1. Okay, a quick example problem. Let's write 20 and 5/9 degrees in terms of minutes and seconds. So 5/9 of a degree, well, there's 60 minutes in a degree, so 5/9 of 60 is 33 1/3. But a third of a minute is 20 seconds. So we'll just write that 20 and 5/9 degrees is 20 degrees, 33 minutes, and 20 seconds. As you already know, angles that are 90 degrees are called right angles, and angles that are less than 90 are called acute, and angles that are bigger than 90 are called obtuse. And also, angles that are bigger than 180 are called reflex angles. A straight angle is just a 180-degree angle. And two really important facts, two angles whose sum is 90 degrees are called complementary. And the angles don't have to be right next to each other to be complementary. They just have to add up to 90. They don't have to be right next to each other. And also, angles who add up to 180 are called supplementary. And it's also really important to know that angles are often named with Greek letters. So you can use most often theta to represent an angle, but also you could use phi, alpha, beta, etc. Okay, so if we have two lines, any two lines whatsoever that intersect, they're going to be called, the lines are intersecting, but there's always what we call vertical angle pairs in intersecting lines. So you can kind of see in this picture, since a line has 180 degrees, angles alpha and beta, which together form the line, are supplementary. Thus, alpha plus beta is 180 degrees, and similarly, the other two angles, alpha and theta, are 180 degrees. And from those two equations alone, algebraically, you can deduce that theta must equal beta. So there's a quick little proof that vertical angle pairs are the same measure. So they're always equal to each other. In any intersecting line situation, you know that vertical angle pairs are going to be equal. So down here is a really common picture that you see a lot. You have two parallel lines, line L and line M, and then you have what's called a transversal. Now line N is called the transversal here. Angles alpha and beta here are called alternate interior angles, and they are always equal. So alpha and beta there, alternate interior, they're equal. Since gamma and alpha are vertical angles, they're going to be equal. And also because beta was equal to alpha, alpha is equal to gamma, gamma is equal to beta, and gamma and beta are called corresponding angles. Also, theta and beta together form a straight line and thus are supplementary. Since beta is equal to alpha, we find that theta and alpha are also supplementary, and the angles theta and alpha are sometimes called same-side interior angles. So all of that is super important to know. Whenever we have parallel lines in a transversal, this always applies. And you can even prove to yourself or justify why alternate interior angles and corresponding angles are the same. All you'd have to do is just write down the supplementary pairs, and you can algebraically deduce that those angles must always be the same measure. Okay, one quick point. There's this parallelogram up there. Whenever you have that two angles are the same, we can always denote them as equal by drawing those little circle things. So if there's one little arc, it means that those two are equal, and if there's two arcs, it means that those two are equal. But the one arc angle is not necessarily equal to the two arc angle. Just as we do for lengths, if we have one tick mark, those two are equal, and there's two tick marks, those two are equal. And okay, so down here is a nice little proof that the sum of the angles of a triangle is always equal to 180 degrees. And this uses the two parallel lines in the transversal that we had on the last slide. So make sure to read this proof closely. Its usefulness is that we're going to add a parallel line. We're going to think of, okay, so line segment ED is parallel to line segment AB. Okay, we're just going to draw in, starting at C, we're going to draw in that line that is parallel to AB. So ED is parallel to AB by construction. So we're calling that line L. And then we have that Alternate interior angles. We have angle BAC is equal to angle ACE. We also have that angle ABC is equal to angle BCD. And since angle ACB, ACE, and BCD together make up a straight line, they all add up to 180 degrees. And so therefore, alpha plus gamma plus beta is equal to 180 degrees. But alpha, gamma, and beta were exactly the angles inside of the triangle. So those add up to 180 as well. So that's a neat little proof. If you've ever wondered why a triangle, the degrees add up to 180, it's because they add up. It's because of this picture, basically. Okay, so let's move on a little bit to another topic called exterior angles. So we've talked a lot about interior angles and just regular angles, but there is something called an exterior angle. So the following picture, let it describe it. So we have this triangle with angles alpha, beta, and gamma. Now the angle theta there is called the exterior angle to gamma. So an exterior angle is not an angle that makes the other angle add to it to get 360. It's going to be the supplement angle, basically. And we have a proof here called the exterior angle theorem that if you add up all of the exterior angles of any polygon, you're going to get 360 degrees. Oh, excuse me, this is a different theorem. So yeah, so this is for a triangle. If you have one exterior angle, prove that that angle is equal to the other two angles. So for instance, prove that theta is equal to alpha plus beta. And we can see this because alpha plus beta plus gamma equal 180 because they're in a triangle, and gamma plus theta equal 180 because they're supplementary. And if you combine those equations, you can deduce that alpha plus beta must equal theta. Okay, so we have an exercise here. This is the theorem I was talking about. Let alpha, beta, and gamma be exterior angles of angles A, B, and C of triangle ABC. Show that the sum of those angles is 360. So I'll let you work on that for a little bit. So we have an important proportion when we talk about circles, arcs, segments, and sectors. So you see this here, we have a picture, we have circle O, and we have a sector. We have an angle theta, and we have an arc theta right there. So arcs can have measures too. The measure of an arc is just the amount of degrees that the central angle subtends to get that arc cut off. And so this equation right here is just saying that arc AB, the measure of it, if we divide it over 2 pi r, the length of that arc AB divided by 2 pi r, which is the circumference, is going to be equal to theta over 2 pi, which 2 pi is the number of radians in the whole circle. So theta is in radians. So given this, we have that arc AB, the length of the arc, is equal to r times theta. And there's an important equation you'll want to write down. The arc length of an arc is the radius times the central angle that it subtends. And therefore we can get a formula for the area of a sector. Theta, the measure of the sector, is, if we take that over 2 pi, that's going to be the fraction of the entire circle that we're going to have. So we can just take that times pi r squared and get r squared theta over 2, and there's a nice little formula for the area of a sector. We can also find the area of a circular segment, and if you remember, a circular segment is when we have a chord cutting off a piece of the circle. We can just take the sector minus the triangle there to get the area of the circular segment. And I've been saying central angle a few times. A central angle is just an angle that is formed by 2 radii. So we've already seen how angles can be measured by the arcs they cut off of circles centered at the vertex of the angle. A central angle is just when we have 2 radiuses and they cut off a certain arc. That angle that those 2 radii make with each other is called the central angle. Okay, here's 2 really important results that you may or may not have seen before. The first result is that whenever we have a circle and we have an angle there, where the angle, we have a point on the circle B, and it's making an angle, ABC, where AC is an arc. The measure of the arc AC, so the number of degrees in that arc, divided by 2 is going to be the degrees in ABC. In other words, we say that an inscribed angle B has a measure of 1/2 of the arc it intercepts. And the next result is if we drag that point B out a little bit so that it's outside the circle, we get another fact. And this is that the measure of the angle BAC there is going to be alpha minus beta over 2, where alpha and beta are those arc measures there. Okay, so we have a couple more results. Here we have a circle, and we have a chord, and then we have a tangent line that's drawn at one of the endpoints of the chord. This is saying that angle ABC is going to equal theta over 2. And that theta there, the theta is the arc that angle cuts off. So it's going to be that big arc there, arc BC, the major arc BC there. So angle ABC is equal to major arc BC over 2 there in that picture. And then the next one, a little bit easier to understand, the angles formed by 2 chords. Now, they don't have to meet at the center of the circle, they can meet anywhere in the circle. If you have 2 chords, no matter what they are, they intersect. Theta there, the angle formed when you intersect those 2 chords, is going to be equal to alpha plus beta over 2, where alpha and beta are those two arc measures. So right away, we can apply these angle properties in circles. Let's apply it to this first example here. We're going to show that any inscribed angle which subtends a semicircular arc is a right angle. So let's parse that and figure out what that means. So remember, an inscribed angle is an angle that is appearing on the edge of a circle, and then it subtends a semicircular arc. That just means that the arc it subtends is 180 degrees. So we're going to see a picture of this in this following example. So let's take a look. So we can use that first property there. Because the angle that is cut off is 180 degrees, it's a semicircular arc, so it's 180 degrees. The measure of that angle there is just 180 over 2, which is 90 degrees. So therefore the angle is a right angle. And this is super important because what if we completed it so that it made a triangle there? So the inscribed angle, that's our angle measure, it's 90 degrees. Let's just draw the hypotenuse in. Thus, any inscribed triangle in a circle that one of the angles is a hypotenuse, or one of the sides is a diameter, that's what's happening here, right? If you have an inscribed angle subtending a semicircular arc, the semicircular arc is 180 degrees, so that's halfway around the circle. So if you connect those 2 points there, you're going to get a diameter. Okay, so let's take a moment. Let's show that any diameter drawn from the point of tangency of a tangent line L is perpendicular to the line. Now we said this before. We said that if we drew a tangent line and then we drew a line that went through the center of the circle, in other words, the diameter goes through the center of a circle, that it's perpendicular to that tangent line. So let's go ahead and show that, and we can show it using these results that we just have for circles here. Okay, so here we have the picture here. So angle CAB, that is the angle that we're trying to show as a right angle. It's formed by the tangent line L and the chord, but the chord is a diameter of the circle, but in particular, not in particular, but it is a chord. So if you remember, one of the results that we talked about is that the measure should be half of the arc it cuts off. Well, what's the arc it cuts off? It's 180 degrees. So since the chord there is a diameter, the arc is going to be half the circle. So the measure of angle CAB is 180 degrees over 2, which is 90 degrees, and thus line AO is perpendicular to line L. Okay, so let's move on to what we have finally for this class today, and that's going to be a collection of problems. So I hope you can read this. Your homework tonight is going to be to do these 4 problems here. Exercise 10-2, Exercise 10-3, Example 10-7, and Example 10-8. Now all of these problems can be solved using what we talked about today, so make sure you have all of those results handy to be able to reference so you can solve these problems. And yeah, so good luck with these problems. I'll give you some time to work on this, and then I'll post another video tomorrow. Okay.